So actually, before the graphing, let's talk about function notation just for a minute. I know we've already, listen, fairly certain I've used function notation kind of here and there. So instead of writing y equal to something, y in the equation, we often write f of x, meaning that the value of y depends on x, on the value of x. Or is a function of x. And this notation really has some advantages. Now, I will say most people, myself, you all, will eventually, if not already, really go back and forth between writing y or f of x depending on what's more convenient. Sometimes it's really nice to write y. Sometimes it's nice to write y of t, like when we're talking about exponential growth and decay. Sometimes it's nice to write f of x. Here's one example. Let's say we had y equal to the parabola written in the vertex form, x minus 2 squared plus 3. And the thing about this is it's really kind of messy, for lack of a better word, to write out what a pair of points is, meaning I know that if x equals 1, y would be, so I'm going to plug in 1 for x and get 1 minus 2 quantity squared plus 3. That's negative 1. Negative 1 squared is positive 1. 1 plus 3 is 4. But it's kind of a lot more writing than I would prefer to do. On the other hand, look at this. If we write that f of x is equal to x minus 2 squared plus 3, I'm going to call it in here. If we write it this way, if I want to know what happens when x equals 1, we'll check it out. F of 1 is equal to 1 minus, right? It's the same computation. 1 minus 2 squared plus 3, which is 4. So here's what I think is kind of great. F of 1 equals 4 tells you the same information as saying x equals 1 and y equals 4. This says, oh yeah, when you plug in 1 for x in the function, you get y, the function value, equal to 4. So this is just convenient, right? It's a nice way of writing things that gives you kind of all the information in one compact statement. There are a lot of other reasons we also like function notation because it's easy to manipulate. You can do a lot of things with it, but this is one of the things I always think of. So yeah, so you definitely, I mean, calculus the next quarter, although definitely about rates of change. It's all done in the language of functions. So it's going to be super duper important to get very, very comfortable using this functional notation. That's what we're going to be doing in class. Maybe not all the time, certainly a lot of the time. You know, as I say this, I'm looking at the next examples and they're all written as y equals something. So we'll write down both. So what I want to talk about now is just introducing some new functions. I would imagine some of you, many of you have seen some or all these before. We've talked so far in this class about how to graph lines and parabolas and circles, circles not being a function, still an important equation to be able to graph. Now let's learn a few more graphs. So more graphs. And, well, no. I would say, just to kind of actually back up for one more moment. So when I talk about lines and parabolas, there are two specifically that I would like you to keep in mind. Let me erase this here. And the ones that we keep in mind are the line y equals x, which just looks like this. That one's not super duper important. Oh, it's not important. And then the parabola y equals x squared. These are kind of the most generic versions of these graphs, or as we often call them, they're the parent functions. They're the line and parabola that you can kind of build any other line or parabola from. And that's going to be the same with the next functions we introduce, is they're going to be the quote unquote parent functions of all the other types of functions of the same type that we can graph. So the first one I want to graph is the square root function. And this actually says a lot about why we make the square root work the way it does. So you'll have to correct me if I'm wrong, but I believe we've talked about how when you take a square root of a number, you get the positive value out, right? Like the square root of 9. What's the square root of 9? Well, it's just 3. It's not plus or minus 3. And again, I think I've said this before, but I could be wrong. I could have said it in a different class. But the point is that when you take a square root of a number, we want to get just one value out, not 2. And the reason why that is because we want the square root to be a function. And to be a function, you have to have the property of it. When you put in one thing, you only get one thing out. So here's the square root function. It's just f of x equal to the square root of x. And we can definitely graph it. So when I graph the square root function, if I'm trying to graph it somewhat nicely, I pick a better pen is what I do if I'm trying to graph it nicely. I think I've exhausted all my black pens. My favorite ones. Do I have any more over here? So let me grab a pen. Cool. So if I'm trying to graph the square root function semi-nicely, I typically plot some points. I pick nice, easy values of x, meaning values that are easy to take the square root of, like 0. That's not where I put the 0 though. I put it down in the, here are my x values, here are my y values, which is the square root of x, right? Using y and f of x interchangeably. So my x values, I could plug in 0 for x, and y would be the square root of 0, which is 0, which would give me this point here. Or I could plug in 1 for x. You get the square root of 1, which is 1. So you have the point 1, 1. You can plug in 4 for x. I'm just cherry picking the nice values. And the square root of 4 is going to be 2. I can plug in 9. The square root of 9 equal to 3. So when I'm trying to graph the square root function, I'm going to pick those points, right? The point 0, 0, 1, 1, 4, 2, and 5, 6, 7. Okay, fine. 8, 9, 3. And we see that as the x values get larger and larger and larger, the y values correspondingly get larger. It looks kind of like this. I'm never good at graphing it. There we go. Now, that's not to say we couldn't pick other values for x, right? We could pick x equal to 5, and then y would be the square root of 5. Whatever that is. It's about, I don't know, 2.2, 2.3. But if I plugged in 5, right, I'd have some, right? This is the point 5 comma the square root of 5. It's not going to be a point I usually pick to graph it because I don't really know off the top of my head what the square root of 5 is equal to. Whereas I know the square root of 4 is 2. I know the square root of 9 is 3. I should also point out that negative values are no good. We can't take the square root of a negative and get a real result. The square root of negative 4 is not real. So we see negative 4 is not in the domain of this function. A few things about this function. So when I'm usually drawing it, if I'm not trying to draw it super precisely, like if I said, I'm going to do this every second. If I said draw the square root function and didn't say like, do a really good job, I would say, okay, square root function, I would start to the origin, and then it kind of looks like this. That's what I would draw. And I would know it kind of looks, in fact, not kind of, it exactly looks like half of a parabola turned on its side. Right there, here's the other half of the parabola, that we actually don't get. But that's what it looks like. So you're trying to be not super precise, you can do it that way. Or you can plot some points. I like plotting a few points. A few things to know about this function. The domain. So the domain is all the things x is allowed to be. And here the domain is that x is greater than or equal to 0. Right? We can't plug in a negative number because we can't take the square root of a negative. In a similar way, the range is all the y values, or all the function values. The range is also everything greater than or equal to 0, right? All the y values have to be positive. There's no y-axis, there's no x-axis. So you can say the range is where the y's are greater than or equal to 0, or you could write it as f of x greater than or equal to 0. Or you could write it as the square root of x, right? That's what's true. The range here is that all the y values are positive, are non-negative, right? Because we also get 0. There's a square root function. Not a lot else to say about it at the moment. Looks like this. These are the allowed x values. These are allowed y values. That's kind of all there is. Yeah. This is a function we're going to manipulate in a few minutes after we talk about two other functions. Or the graphs of two other functions. Okay. So here's another one that comes up quite often. The absolute value function. So the absolute value function is either, if you prefer, y equals the absolute value of x, or f of x equals the absolute value of x. A couple things about the absolute value. It's always going to give you a positive result. Some people like to define it as the, it's really just how far the number is from 0. That's another way people say it. So if I am trying to graph things, we're trying to plot some points, my x's and my f of x's, the absolute value of x. If I plug in a positive number, I'm just going to get the same positive number back. So if x is, something like 4 or 3 or 2 or 1 or even 0, the absolute value of 4 is 4. The absolute value of 3 is 3. The absolute value of 2 is 2. So whenever you plug in a positive number, you get the same corresponding positive number back. So if I make some little marks, this is where you have to kind of try and space them out evenly. If I plug in 0, I get out 0. If I plug in 1, I get out 1. If I plug in 2, I get out 2. If I plug in 3, I get out 3. So this looks like this. And for any positive x value, we can see that we're going to get the same positive y value. On the other side, for the negative x values, so if x was, say, -1, the absolute value of -1 is +1. Or another way to say it is, how far is -1 from 0? Oh, it's 1 away from 0. So the absolute value is +1. People also kind of talk about the absolute value as a distance. It gives you the distance from 0. I know I already said that. I'm saying it again. And we're going to see the same sort of thing. If I plug in -2, the absolute value of -2 is +2. So we're going to plug in -2, you get +2. And so we can see that no matter what negative value we plug in for x, we're going to get the corresponding positive value for y. So this is your absolute value function. The domain, well, there's nothing x is not allowed to be, right? You can take the absolute value of any positive or negative number and get the same corresponding positive number out. So we can't, so I assume when you mean if we plug in negative infinity, Jesus, is that what you're saying?
Yeah.
So the thing is, you can't really plug in negative infinity. I mean, you can kind of, but negative infinity is not a real number. So we can't actually evaluate a function there and get a real result. But we can see that as x gets more and more and more negative, the y values get more and more and more positive. So you could kind of say that if you plugged in negative infinity, the y value would be positive infinity. That's kind of what's happening if you want to try and answer that question.
Okay, thank you.
You're welcome. For the domain here, I would say the domain is all real numbers. X can be literally anything. The range, well, just like before, actually, the y values still have to be greater than or equal to 0. So we can say the y values are greater than or equal to 0, or if you prefer the function notation. And then something else that comes up a little bit later, but I'm going to say it now anyway. Absolute value function is a piecewise function, meaning it's defined to be two different pieces in two different domains. So over here on the right side of the y-axis, that's the line y equals x. Over here on the left side, what line is that? Y equal to, any guesses? It's okay if you don't guess this. Negative x, exactly. So people often write this absolute value function in the following. So this is not something we're going to talk about right now in great depth, but I will just point out this comes up later. We can also say that the absolute value of x function is equal to the piecewise function, where it's equal to, well, here if x is positive, right, x is positive over here, it's just equal to y equals x. But over here, if x is negative, well then the y, the absolute value of x, the function, is equal to negative x. And then you can pick 0 to go with either one, right? Because whether it's equal to negative x or positive x, when you plug in 0, both of those are 0. So we can just tack on the equals to right there. So this is a way that people define the absolute value as a piecewise function. And it actually comes up quite a bit. Especially when we start talking about if a function is differentiable. I know it's next quarter. But I try to at least start kind of talking about how things are going to come up as you see them in future classes. Okay, the last graph we want to mention before we start graphing things more is, actually, what is it? What is it? I think it's the cubic. Yeah, it's the cubic, okay. So, cubic function, which I will freely admit I'm not great at drawing. I've gotten better over the years, but it's not my best. So it's the function y equals x to the third power, or if you prefer, f of x equal to x to the third. We can again plot some points. There's usually 5 specific points I like to plot. And usually when we're plotting points, we're trying to pick things that are easy, right? I'm not picking x equal to 1.7, even though I totally could, right? 1.7 cubed is some real number. It's not a nice number, but it is some real number. But no, I'm going to pick the easy things. I'm going to pick x equal to 2 and 1 and 0 and negative 1 and negative 2. Try and pick things that aren't going to get too big or too negatively big. So if x is 2, 2 cubed is 8. X is 1, 1 cubed is 1. X is 0, 0 cubed is 0. X is negative 1, negative 1 cubed is negative, right? It's the negative into negative into negative. Similarly, negative 2 cubed is negative, because it's a negative into negative into negative, which is going to be negative 8. And then we can try to plot this. I always feel like my graphs, when they get really big fast, I don't make them look quite as steep as they should. But let's see. So if I go over 1, 2, over 1, 2, and then up 2, 3, 4, 5, 6, 7, 8. So I've got the point 0, 0, 1, 1, 2, 8. And then negative 1, negative 1, and then negative 2, negative 8. It's gonna look kind of like this. Gotta make noise when you graph it. Kind of like that. That's all right. You have graphing utilities at your disposal, right? Maybe a graphing calculator, definitely Desmos on a computer. So while this looks fine, you could certainly see a more precise looking version of this in lots of places. I will also say, for this function, the domain, well, x can be anything. So the domain is all real numbers. The range is also all real numbers, right? Y can also be anything. So those are 3 new parent graphs. And in a minute, in a couple minutes, we're going to start manipulating these by shifting them up and down and left and right, or flipping them horizontally or vertically. I think that's it. Maybe stretching them, but I think we save stretching for next class. Stretching is always kind of interesting. So yeah, I'm going to want multiple colors here. Yeah. Okay, so what do negative signs do? So what does a negative sign do to the graph of y equals f of x? Well, it depends on where it is. So there's 2 answers. And so I'm going to say a general statement here, and then I'm going to keep referring back to it as we go along. If you do something to the outside of the function, meaning if I put the negative outside the function like this, that's typically always going to affect the function in a vertical way. On the other hand, if we do something inside the function, meaning we do something to x before we apply the function to it, it's typically going to affect the function in a horizontal way, like this. So here I'm doing the negative to x, and then I'm doing the function afterwards. We do read functions from the inside out. Right? I see x, and then I get negative x, and then I get the function of negative x. Whereas here, I have x, then I have f of x, then I have the negative of that. So this is going to, this here is going to flip the function across the x-axis. Whereas this one, this is going to flip the function across the y-axis. Let's look at a couple examples, some easy examples. So let's look at, say, for example, y equal to the function x squared versus y equal to negative x squared. Sorry, I'm taking my function f of x equal to x squared, and I'm saying, okay, here's the regular one. We know what that looks like. Y equal to x squared is your good old upward opening parabola. There's y equal to x squared. But if you do y equal to negative x squared, you're putting a negative on all your y values, right? So in fact, let's make a little table here. X squared, negative x squared. So if x is like your usual kind of 2, 1, 0, 1, 2. 2 squared is 4, 1 squared is 1, 0 squared is 0, 1 squared is 1. Oh, sorry, I forgot the negatives. Sorry. Negative 2 squared is still 4. Negative 1 squared is still 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. But now, if you put a negative on that after you've already squared, which right then, right, if you look at negative x squared, it's really important to realize that we do the squaring first and the negative after. So negative 2 squared is 4, but then negative 4 gives you a negative 4. And then here we're going to get a negative 1 and a 0 and a negative 1 and a negative 4. So if we graph negative x squared, it's actually the whole same parabola, but flipped over, opening downwards. Like that. So when you slap on a negative sign in front of the entire function, it flips it over vertically. Do I have enough room over here? I might have enough room over here. On the other hand, when you put a negative inside the function, or I often say inside the function, but I also say when you put a negative on x before you apply the function, it's going to flip it horizontally. Let's look at, I think I've got enough room up here. Let's look at, so f of x, let's look at f of x equal to x plus 2. Just a straight line. It goes up from left to right. It's got a y-intercept of 2. It's got an x-intercept of negative 2. So here, 1, 2, 1, 2. There's my f of x equal to x plus 2. But now if I change my x to a negative x, all right, f of negative x, well, I'm going to substitute in the negative x for x. So I'm going to get negative x plus 2. And although we know we're supposed to flip this across the y-axis, I'm really just going to graph it like a line. So I try and graph this like a line, where I'm getting y equal to negative x plus 2. It still has the same y-intercept. If I set x equal to 0, you get y equal to 2. But the x-intercept has now flipped, right? Here, in the previous one, the x-intercept was negative 2, because if y is 0, negative 2 plus 2 equals 0. But here, now the x-intercept is positive 2, because if y is 0, then x has to be positive 2, because the negative 2 plus 2 will equal 0. So look, I draw it right. The graph flipped. It was going like this, and then it flipped across the y-axis, and now it's going like that. So that is the effect of putting a negative sign inside or on x before we do the functions. It flips it horizontally. If we put a negative outside, it flips it vertically. That's kind of the whole idea with these flips. Or more mathematically, these reflections. So this is a flip across the x-axis or a reflection across the y-axis. This is a reflection across the x-axis. This here is a flip or a reflection across the y-axis. Okay. Erase this side over here. So we can use this to graph other things. For example, if I want to graph, say, y equal to the negative absolute value of x. Well, I know that the absolute value of x is a V shape opening upwards. So here is f of x equal to the absolute value of x. I know we literally just graphed this one. I'm just going to graph it again. It looks like this. And now y equal to negative f of x, which is the negative absolute value of x, is going to look like that V, but flipped over the x-axis or reflected over the x-axis. If you're not sure, it's always fine to plot some points, right? We could totally make a table, say here's my x, here's my negative absolute value of x. If I plug in things like 3, 2, 1, or 0, the absolute value of 3 is 3, but then I get negative 3. Or 2, I get negative 2. Or 1, I get negative 1 or 0. And it's even true when I plug in negative values. Right? The absolute value of negative 1 is 1, but then I get negative positive 1. Opposite value of negative 2 is positive 2, but then I get negative positive 2. And so I can see that I've got things like 3, negative 3, 2, negative 2, 1, negative 1, 0, 0, negative 1, negative 1, negative 2, negative 2, and so on. And then you can graph something like y equal to the square root of negative x. So since the negative is happening before the square root's happening, we're going to, oh, I know there were some words I used to say last time that I think are good. I'll say this in a second. We know that we have to flip across horizontally. So instead of looking like this, there's my usual, that doesn't look very good. There's my kind of usual square root function. It's gonna flip across the y-axis and look like this. Yeah. I've drawn better. And so here's kind of what I'm thinking about when I look at these. What I can see when there's a negative on the outside of the function is the x values all stay the same. I lost my absolute value, sorry. So right, I picked my same usual x values, and if there wasn't that negative sign, I would get my usual y values, but that negative sign changes all my y values to the negative of what they were. So when you have a negative on the outside, you get all the opposite sign y values, which means you flip over. On the other hand, if you have a negative on the inside, well, now you're having to change your x values to get the same usual corresponding y values, right? If we were doing y equal to the square root of x, my usual choices for x would be 0, 1, 4, 9, because those are the easy ones. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. But the problem is now if you've got y equal to the square root of negative x, you have to adjust your x values so that you still can get the same y values. If x is 0, negative 0 is still 0, and the square root of 0 is still 0. But now x can't be 1. Right? If x were 1, you would get the square root of negative 1, which is not real. So x has to be negative 1 so that we get the square root of negative 1, which is the square root of 1, which is 1. And x has to be negative 4 so that we get the square root of negative 4, which is the square root of 4, which is 2. So right, we get x being negative 1, y being 1. X being, negative 4, y being 2. That's what's happening here. And that's kind of the idea with all these transformations is if you're transforming something vertically, you're leaving the x's the same and you're seeing how y changes. If you're transforming something horizontally, you're trying to figure out how do I change the x's to still get the same y's that I had before. Okay.
Can you repeat when you're changing vertically that sentence that you were saying earlier?
So when you're changing vertically, the x's are staying the same. Like you're picking the same x values and you're seeing how the y values differ. In this example, the y values are the opposite signs they would have been, right? If we were just graphing f of x equal to the absolute value of x, we would pick these x values and the y values would have been positive. But since it's a negative absolute value of x, now the y values have all changed to be negative.
Thank you.
You're welcome. And that kind of idea is going to hold whether we're doing whether we're doing reflections like we were just talking about, or whether we're doing shifts like we're about to talk about, or we're even stretching or compressing like I think we'll talk about tomorrow. So let's look at some shifts. So the question on this next page here is, what does adding a number do to the graph? And again, it's going to depend on where we add. So if we add outside, like this, y equal to f of x plus d, that's going to shift the graph vertically. So this shifts the graph vertically. Specifically, it's going to shift it up if d is positive. It's going to shift it down if d is negative. And I think let's do an example before we talk about the horizontal one. So, and I'm gonna change the example there slightly. So let's say I want to graph, let's graph f of x equal to the square root of x plus 3. So what's going to happen here is I'm going to take my usual square root graph and everything's going to move up 3. But we can kind of also see this, right? If I make a table again of my x values and my y values, right, let's make a 3-part table. I'm still going to pick my usual nice x values, 0, 1, 4, 9, etc. Right? And again, you're not limited to these. You could actually pick any positive number for x, but these are the nice ones. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. And then here, I'm just taking the same square root and then adding 3. So square root of 0 plus 3 is 0 plus 3. Square root of 1 plus 3 is 1 plus 3. Square root of 4 plus 3 is 2 plus 3. Square root of 9 plus 3 is 3 plus 3. So all of my previous y values from my parent graph got increased by 3. So I'm just taking my whole graph, which would normally look like this. Right, here's my dashed parent graph. Right, there's my usual square root function, but now it's all going to get lifted up 3. I'm going to get the point 0, 3, and the point 1, 4, and the point 4, 5. So it's the same graph, we just moved it up 3. And if I had done square root of x minus 2, it'd be the same graph, but all shifted down 2. So again, the x values stay the same, the y values get changed when you do something outside the function. Okay, what if we do something inside the function? I will also point out that aside from the reflections, the other inside the function things can be somewhat counterintuitive. So let's say we're going to adding a number inside the function. So we've got like y equal to f of x plus c. So we'll say the things first and then we'll do an example. So this is going to shift the graph horizontally. Now here's the thing that's maybe slightly counterintuitive. If c is positive, so this is like x plus 2, for example, it's going to shift the graph 2 to the left. So if the thing you're adding is actually positive, then we're going to shift it to the left. And if c is negative, we're going to shift to the right. And I think we can explain this fairly well through an example. So yeah, let's look at another square root example. I like the square root function because it doesn't have any symmetry. Let's say I want to graph y equal to the square root of x plus 2. So that's going to shift it 2 to the left. Now let's take a look. How do I usually say this? There's a way I've done this before that's worked out really well. I feel like I'm going to fail here. So here's what I'm going to list before I do anything else. I'm going to list the nice values, right? We know we want to plug in, or I should say, I'm going to cover this up. We know we want to take the square root. We want to take the square root of nice square numbers, like 0, like 1, like 4, like 9. Right? Those are the numbers we want to take the square roots of. But the thing we're taking the square root of is x plus 2. So we need the x plus 2's to equal those. Okay. Well, then we can say the square root of x plus 2 is really nice. Right? The square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. But then we're not trying to plot x plus 2 versus y. We're trying to plot x values on the x-axis and y values on the y-axis. So I actually need to go back and say, well, okay, if x plus 2 is 0, x had to be negative 2. Right? X had to be 2 less than it would have been because we're adding 2 to it. And if we want x plus 2 to be 1, then x has to be negative 1. If we want x plus 2 to be 4, x has to be 2. If we want x plus 2 to be 9, x has to be 7. So since we're adding on the inside, x has to be that much less so that we still get the same y values at the end of the day. So that's why when you add on the inside, you end up shifting to the left because the x values are going to be smaller to compensate for adding on the inside. So what does this look like? Well, our graph is going to look like x is going to be negative 2, y is going to be 0, x is going to be negative 1, and y is going to be 1, x is going to be 2, and y is going to be 2, and x is going to be 7, okay, 4, 3, 4, 5, 6, 7, sure, y is going to be 3. So they look like this. It just looks like the regular, my bad drawing notwithstanding, it looks like the regular square root graph scooched over 2 to the left. So when you add on the inside, it's going to shift it 2 to the left, or however much to the left. When you subtract on the inside, it's going to shift it that much to the right. Yeah. Okay, we got 2 minutes left, not really a lot of time. Let's do one example, and then we'll finish this up tomorrow, and then we'll do K as well. So here's the example that's actually on this page. Let's graph f of x equal to the square root of x plus 1 plus 4. So here's what I'm going to do. I'm going to take my usual square root graph, which I know starts at 0, 0. You don't really need to graph any more than one graph. But we know it looks like that. And then we're going to shift it 1 left and 4 up. So my graph is actually going to start here at the point negative 1, 4. Right? I took the usual starting place of 0, 0 and moved it left 1 in the x direction and up 4 in the y direction. And then it just has the usual look. And you could plot a few more points if you wanted to, right? If x is 0, square root of 1 is 1, 1 plus 4 is 5. And then you could pick x equal to 3. If x is 3, 3 plus 1 is 4, square root of 4 is 2, 2 plus 4 is 6. You don't need to plot any of these extra points. You do need this first one, though, because that's kind of like the beginning, and we need to know where that is. But that's kind of the idea really behind shifting graphs, is that you're kind of seeing where, well, in fact, let me do one more because I've got still a minute. If I wanted to graph, say, f of x equal to, in fact, this is going to be kind of nice. Let's say x minus 2 squared plus 1. Well, that's my usual parabola, y equals x squared, shifted 2 to the right and up 1. That's why that's the vertex form, right? Because when you take your vertex at 0, 0 of your parent graph and shift it, this shows you where the vertex ends up being. So we're taking our parabola, shifting it 2 to the right and up 1. So there's our new vertex, and it looks like your usual parabola. All right, we moved it over 2, up 1.